Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue on for a college algebra course into a review of exponential and logarithmic functions. If you don't know, there's a video right before this called a brief review of exponential functions. In this video, we're going to talk about the types of exponential growth and decay, because in the last video we defined what exponential growth is and what exponential decay is. It's based on literally the base of the exponential function. But now we're going to really dive into the different kinds of exponential growth and decay that you can see and that you have seen in problems in the past. We're going to try to wrap it together, put a nice little bow on it, so it's a lot easier for you to work with those problems in the future. So let's define some things. Growth and decay factors. The exponential function, p of t is equal to p naught b to the t, has a growth factor. I should say it the other way. I should put the emphasis on growth. Has a growth factor. And I highlighted that right there. It has a growth factor if the base is greater than 1. And we call the growth factor itself b. So it has a growth factor of b if the base is greater than 1. Otherwise, it has a decay factor of b, again, if the base is between 0 and 1. So decay factor if the base is between 0 and 1. That's all I really have on this page, so let's move forward. Now, it's been a while since we've had an example, and that's on purpose because most of this is review, but it's good to kind of have just a slew of examples right from the get-go here. So identify the growth or decay factor. Not only are we going to identify it, but we're going to state whether it's a growth or a decay factor. So let's look at this first exponential function. First of all, the initial population, whatever this is 3.2. It could be $3.2 billion, or it could be 3.2 million people, or it could be 3.2 gallons of ice cream. Whatever it is, doesn't really matter. I always put a story behind exponential problems because I really like exponential problems. Anyhow, the fact that the base on the exponential function is less than 1 tells me that we have a decaying population. So this is a decay factor. And in fact, the decay factor itself is 0.83. Now, let me just tell you, there's a lot of ways to think about this. And I want you to start thinking about these in terms of stories. So this means that every day, minute, month, year, I don't know what T stands for, just depends on the problem, but every time period that passes, you only get to keep 0.83 of the original population. Let me write that down. And forgive me, I zoomed out a little bit too. Sorry about that. I know it gets kind of herky-jerky here. So the 0.83 means that every time period, we only keep 0.83 of the previous population. And because you guys are mathematical experts at this point, you know 0.83 is the same thing as 83%. So this means every day that passes, or whatever T stands for, you're only keeping 83% of the previous population. Another way to think about that is that you're losing 17%. Having that natural understanding of an exponential function is so very important. My goal here is to make sure that you leave your college algebra class with a super strong understanding of these things, because exponential functions really are going to dominate a lot of science and really a lot of news, honestly. So we've already labeled it. I spent a lot of time on that very first one. There was no need for that, but well, there kind of is a need, right? Because I want you to truly understand what these things mean. So let's see, P sub 2. So the second population model we're looking at, we start with 16 objects, and it looks like we have, since this base here, let me highlight it, since this base is greater than 1, we have growth. So this is a growth factor, not a decay factor, but a growth factor. Again, I don't want you to just look at it and memorize, okay, 1.2 growth factor. I want you to think, what does that mean? It means every time period that passes, you multiply your previous population by 1.2. That is, it's growing by a factor of 1.2. Now, there is a really special way of seeing this. So let me showcase how you could see this. If you'll play along with me just for a moment, I'm going to grab this and move this over here. Say that's 16 times 1.2 to the t power. And you could rewrite that as 16 times 1 plus 0.20 to the t power. And what this means is you get to keep your previous population and you get to increase it by an additional 20%. That's really what this means. This population is growing by 20% every time period. Let me zoom out and write that down. So I'm trying to, like I said, hand you a lot of different ways to view things. In fact, that idea of 1 plus can be used in the first example. That first example, whoops, I could have rewritten that as 3.2 times 1 minus 0.17 to the t. Because that's what 0.83 is 1 minus 0.17. And that tells me that I get to keep my previous population. Oh, no. I get to lose 17% of it. So I'm losing 17%. And that's what we wrote down earlier in blue there. You're losing 17% of the population each time period. Those are really nice ways to kind of gather your information here and really make a picture or a story out of this. The next population model. Now this is going to require more handwriting, so I'm going to write it down below. Now, to be honest with you, you should be strongly familiar with everything I'm writing down. You should already know that this is a compounding formula. This is saying that you have $500, for example, that you're investing, and you get to keep all that 500, plus you're going to add to it. What? You're going to add 5%, but it's divided into 12 pieces. In other words, you gain a little bit of a percentage of interest every month for 12 months. That's what this is saying. I get to keep what I originally invested, but I'm adding to that 5% divided by 12 every month for 12 months. That's how you could read that. Anyhow, the fact that it's 1 plus means that base is greater than 1. But here, there's a little surprise. So I know since this is greater than 1, we've got a growth factor. But the growth factor is not that 1 plus 0.05 divided by 12. It's going to require you to recall your laws of exponents, and I really try to drive home the fact that your arithmetic is critical. In fact, well, I wouldn't call it arithmetic. I'd call it your algebra 1. It's critical for your success in all of mathematics. But there is a law of exponents that says the following. B to the nth power raised to the nth power is the same thing as b raised to the mn. So that is powers to powers multiply. So what does that mean in our situation here? Well, believe it or not, this is a powers to powers situation. This is 1 plus 0.05 divided by 12 raised to the 12 and then raised to the t. Now remember what we said about growth factors or decay factors? The growth factor, let me hop back here. The only way you're going to find the growth factor is if you have your exponential function written as a base to a t power. Not a base to 12t, but just to the t power. That would be your growth factor, is what B is, if you could write it that way. So hopping back to our example here, I cannot say 1 plus 0.05 divided by 12 is the growth factor. That's not. I need the exponent to be t, not 12t. So I'm just going to use a little bit of my old school elementary algebra, or algebra 1, to rewrite it like this. This yellow highlighted piece is actually the growth factor. So the growth factor is equal to 1 plus 0.05 over 12 to the 12th power. Now, rather than taking you over to Desmos, I'm just not going to waste the time doing that. I'm going to type it out on my calculator because, well, I don't have this memorized. There's no reason for me to memorize that. So I get the following. This is roughly 1 point, and I'm going to always try to round to 3 decimal places here. So 1.051. That's the growth factor here, 1.051. Again, if you think about that logically in terms of what we are writing up here, like in this example here, we said the growth factor is 1.2, and then we said, guess what that means? Our population was growing by 20% every time period. Well, that's what this is saying as well. This is saying that implies that the population is growing by roughly 5.1% per time period. It's because it's 1 plus 0.051. That's what this is. 1 plus 0.051. And as a percentage, that 0.051 is 5.1%. Notice that if you recall from your elementary algebra and intermediate algebra, if you recall that this is a compounding formula, you know this means that somebody's investing $500 at 5% compounding monthly. And yet, at the very end, we're saying the population is growing by 5.1%. It's because compounding monthly, you get more interest when you compound monthly versus compounding just once a year. So that's why we get more than 5% at the end of the year, because we're compounding monthly. All right. So the growth factor there is 1.051. Let's see what the growth factor is here with this function p sub 4. This is a little bit wackier. I totally get it. But using the method that we had from the previous problem, we could write this as 500 times e to the 0.03 raised to the t power. All I need is a calculator with the e button on it, and I have one right in my hand, so I'm just going to do that. E raised to the 0.03. This ends up being approximately 500 times 1.030 to the t power. It goes on forever, but I just only round to 3 decimal places here. And that being greater than 1 tells me we have a growth factor, and that growth factor is approximately 1.030. I'll write that down. Which means that our population there is growing by roughly about 3%. Now, if you want the exact growth factor is e to the 0.03. All right, let's move on. This last example is most important to me. I find this to be very, very powerful and also very prevalent in the world we live in. Now, going based off of our previous examples, this is definitely a decaying population. In fact, let me use blue for that because I think I've been using blue for decaying populations. So that's a decay factor because you start with a certain population, you keep all of it, but you're losing 2%. So you're losing 2% every whatever. Okay. Or in other words, you're keeping 98%, but I like to say losing 2%. Now, you would be totally wrong if you said the decay factor was a 0.98. That is not true, because we would need to write this while it is a 0.98 as a base right now, the fact is it's not to the t power. We need to write it only to the t power. So what I'm going to do is rewrite this as 0.98 raised to the 1/5 and then raised to the t. Our decay factor is the 0.98 to the 1/5 power. And grabbing a calculator, we find that the decay factor is roughly about 0.996. In other words, every time period that passes, we get to keep 99.6% of the population, or in other words, we lose 0.4% of the population. But there's something more important about this, and that is this: how to interpret this fraction. Notice, and I'm going to write this down below because this is so important. So population model 5. We have 1 minus 0.0, I should probably write it exactly the way I've written it there, 0.02 raised to the t over 5. We lose 2%. We don't lose it. Let's pretend t is in terms of days. We don't lose 2% every day. It takes 5 full days for us to lose 2%. Because if you do the mathematics here, we have this mathematics comes down to a 0.98 to the first power. So we get to keep, after 5 days, 98% of the population. So we've lost a full 2% after 5 days. Well, another way to read something like this is to say we get to, or not we get to, but the result is that we lose 2% of the population every 5 days. So this exponent, very important way to read that is you get whatever this base is, which is decay, so you're losing 2% per 5 days, or 5 years, or 5 months, or 5 weeks, or 5 hours, 5 minutes, 5 seconds, whatever the time unit is. It's a good way to read that. All right, so there's a laundry list of growth or decay factors. And this theorem is just a summary of what I just said. If a population experiences a growth or decay factor of b every n periods, then the per period growth or decay factor is b to the 1 over n. The function for such a process is p of t is equal to p naught times b to the t over n. That is, the population at time t is equal to the initial population times some base, whether it's doubling or maybe it's multiplying by 0.82 or something like that, raised to the t per n days, or n weeks, or n months. I'm just writing days here for an example. Let's go ahead and just throw down a bunch of exponential functions. You should be able to, if you were my student and I was to write out 10 of these, it should take you about a minute to write these down. As far as the answers, these are very fast problems. So let's see. Write exponential functions for each of the following situations. You have an investment. It doubles every 7 years. Well, how would you write that? Well, the population of your money, they didn't tell you an initial population, so I'll just call that P naught. And it doubles per 7 years. That's it. Initial population doubles every 7 years. That's how you read that. You have 50 milligram sample of a radioactive substance. It decays by half every 18 seconds. So the population of that radioactive substance was initially 50. It decays by half, or you get to keep half, every 18 seconds. That's supposed to be an 18. Sorry, it's really small. All right. Another, by the way, you might say, hold on, decays by half, but you wrote half. Shouldn't it be 1 minus a half? If you keep a population and you lose half of it, well, that is a half. So there you go. Finally, a population of coyotes has a decay factor of 0.83 every 10 years. Well, population of coyotes, we don't know what the initial population is, but we do know that it decays, has a decay factor, doesn't decay by 0.83, has a decay factor of 0.83 per 10 years. So every 10 years, it keeps 83% of what it originally had. Now we switch gears, but only slightly, because we've already kind of showcased this. The exponential function, p of t, which is equal to p naught times 1 plus r to the tth power, is said to have a growth rate, and that should have been bolded there. I don't know why I didn't do that, but it's defined to have a growth rate of r if r is greater than 0. Otherwise, it has a decay rate. So all those previous examples where we said, oh, this is 1 plus 0.2, or this is 1 minus 0.17, those 0.2s and 0.17s are called the rates, the growth rates or the decay rates. Let me just showcase that. So in this example here, which was our first example, we saw that we had 3.2 times 0.83 to the t, and we rewrote that later on as 3.2 times 1 minus 0.17. Since it's 1 plus or minus a value, the plus or minus value, or the thing after the 1, is called the growth or decay rate. In this case, because it's negative, that 0.17 is called a decay rate, or a decay rate. Put the emphasis on the first word. So it has a decay rate of 17%. Looking through the other problems, the next one was a 1.2, wasn't it? And I even wrote that as a 1 plus 0.2. Well, 1 plus means you have a growth rate, and the growth rate here is 20%. So every exponential function has two growth or decay statements. The first is going to be a growth factor, which is in this case 1.2. And then the next is going to be the growth rate, which is what comes after the 1. It's the 0.2. So the growth rate is 20%. All of these problems have growth and decay rates. They're just not explicitly written. But for example, this compound interest problem that we took a look at, we said the growth factor was that number right there. And that number was roughly 1.051. But I could write that as 1 plus something. And the plus part is the rate. So that is a growth rate right there that I've highlighted. Growth rate. So again, each time you're given an exponential function, you have both a factor and a rate associated with that function. And depending upon the question, you'll have to answer one or the other. Let's continue forward with some authentic examples. Build an exponential model if a bird population is growing at a rate of 3% per year. Again, I didn't hand you the initial population. So you'd say, I don't know the initial population, but I know that it's growing at a rate of 3%, and that's every year. Normally you would not leave it like that, by the way. You would go ahead and do the arithmetic and say that's p naught times 1.03 to the t power. But anyhow, I kind of like it, honestly. For me, I like to write it like this just because I can easily see that I keep keep the original population and I'm gaining 3%. It's just kind of a nice way to see it. All right, let's go ahead and try the second one. We have a bird population that's decaying at a rate of 11%, and that's every 3 years. So you have a population of birds, started off at some initial value, and it's decaying at 11%, and that's every 3 years. You see how quickly you could write these? It just happens very fast. Finally, oh, by the way, I suppose you could clean that up, right? So that's p naught times 0.89 t over 3. Another way you could have read that is you keep 89% of the population every 3 years. And finally, we have a bird population that's increasing by 115% every 5 years. So this is often done wrong by people. So we have a population, and here we have the initial population. It's increasing, so you get to keep previous year's population, and you're increasing it by 115%, not by 15%, but by 115%. And that happens every 5 years. So this right here is telling us we're increasing by 115%. A lot of people get that wrong. They read it as 0.15, but it's not. It's going to be P naught 2.15 to the T over 5 power. So just be very careful with that. If you wrote plus 0.15, then your population's only growing by 15% every 5 years. You don't want that. All right, so this is it. This is just me kind of showcasing how to write different types of exponential models, whether for growth or decay, and defining growth factors, decay factors, and growth rates and decay rates, because they're going to be used quite a bit with exponential functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.